Alright, so now we are starting estimation. As I discussed in the previous lecture, given a measurement y, we want to estimate the state x. So here is an example. I have a cart, a pendulum, there is no friction here, there is gravity. I can apply a force on the cart and the pendulum will swing. So there is an x displacement and x dot velocity, a theta angular position and a theta dot angular velocity. This has a 4-dimensional state vector, but the measurement may just be theta. Okay, so you know f of t, the force that you have applied, you know the system parameters, you observe the angle theta of t for a while, and can you say what the state vector was at time t equals t0? This idea is related to the concept of observability. This idea that by observing the output for some period of time, you conclude what the state was. This is different from controllability, and yet it is closely related to it, as we will see. So here a system is called observable if given its model. So the system model, the math equations, knowing the inputs for some time greater than t0, so starting at t0 and then on whatever are the inputs, knowing the output y of t, we can determine the state x at t0 within a finite amount of time. So you will see this finite amount is important. It is the same as controllability, this idea that it has to be done within a finite amount of time. And instead of developing the theory directly, we are going to approach it indirectly through a state estimator. So here it is. This is the system. X dot is ax plus bu, y is equal to cx. Students are sometimes confused about this, and so I am trying to say this slowly. These are equations in our study here, but think of it as the real system. Think that there is actually something with mass, with pressure, with current. Okay, sorry, where's my cursor? Here. So this is the real system. X is a physical variable, u is a real input, a, b and c are known. So we have a very precise mathematical model for the physical system, and y is a real measurement. Okay, so this is y. Now we will do a calculation on the side, so that is why I am putting tilde over here. These are just in my computer, except that the input y is being put into this calculation as a forcing. You will see that these equations are similar to these equations, except there is an added term here, the g times y minus y tilde. This x tilde evolves according to the same matrix A here and here, the same B here and here. It is assumed that this input and this input are identical, but there is an additional forcing, a matrix G multiplying y minus y tilde. Now remember, in the scalar input, scalar output case, y is just a number, right? So if y is just a number, what is G? G has to be a column matrix of the same size as x tilde, which has the same size as x. And the output of this calculated system, y tilde, is cx tilde. This calculation, this is called a state estimator. Remember, u is the same, y is from the physical system, but it enters the calculation. G is a matrix of appropriate size, and if y is a scalar, then G is n by 1. What can we hope to achieve? At most we can achieve that y tilde will go to y. The question is, does that mean x tilde goes to x? Remember, one number becomes equal to another number does not necessarily mean one vector equals another vector. There are more things over here to match. But if x tilde goes to x whenever y tilde goes to y, then we have estimated the state. Let us see if we will succeed. So we define the error vector E as x minus x tilde. I will leave it to you to substitute over here and verify. Then E dot is equal to A times E minus G times C times E. Where did the C times E come from? This is because y is cx and y tilde is cx tilde. So if you pull the c out, then you have x minus x tilde, which is E. So the dynamics of the error E is given by this matrix, and so if the eigenvalues of A minus GC are in the left half plane, in that case the error will go to 0. What is interesting is that the eigenvalues of A minus GC are exactly the same as the eigenvalues of the transpose, that is A transpose minus C transpose G transpose. And now this resembles completely a previous problem that we have solved, which is we were trying to place the eigenvalues of A minus BK by choosing K. Now we are placing A transpose minus C transpose G transpose by choosing G transpose. Okay. Scalar input, scalar output, A is n by n, B is n by 1, that means it is a column matrix. C is 1 by n, that means it is a row matrix. Here is the dynamical system, here is our estimation related system, and you see that these two are closely related. They get transposed over here, the B gets transposed and comes in here, the C gets transposed and goes over there. If this one is controllable, then this one is observable. If this one is controllable, then this one is observable. This duality is something that you can read about. But over here we want to know whether observability is possible, and that just has to do with controllability of this system now. And so we will check, we will make the controllability matrix for this transposed system, but that is the same, we can write it as transpose. We are looking at the rank of a matrix is the same as the rank of its transpose, so we will transpose it, and this is the observability matrix. We can also exchange the position of rows and write it like this, and the question is then, if this is full rank, then the system is observable. So remember the pendulum cart example, right? So if y equals theta, that means the state vector xx dot y dot xx dot theta dot is not measured, only y equals theta is measured. Is the system observable? Okay, that is the question. So next we will do an example of state estimation, but I am going to do that in the next lecture.